This first talk will be given by Amanda Stribe, and she'll be telling us about iterated decomposition of biased permutations via new bounds on the spectral gap of Markov chains. Take it away.
Okay. Hi, everyone. So in this talk, we're going to be interested in analyzing the spectral gap of a Markov chain. And that's the difference between the top two eigenvalues of its transition matrix. The spectral gap determines the rate of convergence to its stationary distribution pi. You can think of it as telling you how long it takes to get to a random state from any start state. We're going to be using the decomposition method, which allows you to analyze the spectral gap in terms of the gaps of simpler constituent Markov chains. Our main application is to a Markov chain on permutations, or really k-particle systems, where you have n particles that are divided into k different classes. So this is an example where k equals 4 and n equals 9. We'll be looking at the nearest neighbor transposition Markov chain, which operates by choosing an element at random and trying to swap it with a neighboring element. So the probability of swapping I ahead of j is given by the parameter pij. In 2003, Jim Phil conjectured that under some natural conditions on the set of Pij, the spectral gap is an inverse polynomial in n, and the smallest spectral gap is attained when all of the Pij's are equal to 1/2. So this problem has been looked at by several people, but it's still open in general. And some of the more recent work has taken an iterative approach. The idea is that if you want to get to a random permutation, you can show that the ones get mixed, and then for any fixed position of the ones, you can get the twos mixing, and so on. So this is just a sort of intuition, and it doesn't work that easily usually. It's complicated by the fact that pi is not a uniform distribution in general. However, we can formalize this intuition by defining a bijection between k-particle systems and pairs A and B. So A will give you the location of all the ones, and B tells you the relative order of all the larger particles. Given this bijection, we can view our state space as a product space, where A tells you the row and B tells you the column, and there's a unique element in your state space in that row and column. Now this iterative idea works great if the chain restricted to A is independent of the chain restricted to B. And in some cases that's true. And there's certain settings of the Pij that make that possible. And when that is possible, you can show optimal bounds of 1/n² on the spectral gap. However, it's not true in general, but what you can do is use the decomposition theorem of Madras and Randall. And it allows you to analyze the overall gap in terms of the gap restricted to A and the gap of a different Markov chain restricted to B. So this allows you to actually get an analysis of the chain. However, it introduces some overhead. And in this case, we actually get an extra factor of 1/n² each time we apply it. So we end up, we're iteratively applying it k-1 times. So we apply it first for 1, then 2, and then 3, and so on. And so you end up with a bound on the gap that is exponential in k. And what we really want is a bound of probably 1/n² for any k. Okay, so our our strategy is to come up with a new decomposition theorem that introduces less overhead for situations like this. So just for a bit of notation, let gamma min hat be the minimum gap over the Markov chain restricted to any row, and let gamma min tilde be the minimum gap over the Markov chain restricted to any column. If the Markov chain were really a direct product of independent Markov chains on rows and columns, then the overall gap would just be the minimum of these two parameters. What we want to say is that if they are nearly independent, then we should get a gap that is close to this minimum. So that's the kind of theorem we're after. But of course, we have to say, what do we mean by being nearly independent? And the function that we use is this R of AB, and it gives you the joint probability of the state AB divided by the probability of A times the probability of B. Now for direct products, R of AB would be 1 for all pairs I and J. And we're going to require that R of AB be close to 1 on average. And this is important because for our application, R of AB can actually be exponentially large for some pairs or exponentially small. So to show that R of AB is close to 1 on average, we want to show the following quantity epsilon is close to 0. Epsilon is essentially an expected value of this function in parentheses. So if R of AB were 1, we would get 0. And if R of AB is very large or very small, this ends up being very large. However, it's weighted by the probability of that state. And what we show is that the overall gap is at least the minimum gap that we want times this extra correction factor that depends on epsilon. And we prove some generalizations of this theorem. I'm presenting the simplest case here. If you're interested, go look at the paper. So finally, we apply our decomposition theorem to the biased permutations problem. And we show that if there are at least log n particles of each type, then at every level of the iteration, epsilon is at most 1 over n squared. And this allows us to apply the decomposition theorem iteratively, order n times, and still get a nearly optimal up to constants bound of 1 over n squared. Okay, I'll wrap it up there. Thanks.
All right, thanks, Amanda. So now we'll be taking questions, and let's experiment with just unmuting yourself if you have a question to ask a question. Okay, maybe I can just kick it off with a question. So are there other natural applications for your decomposition theorem outside of permutations?
So we hope so. In the paper, we outlined sort of a simple application for the one-dimensional Ising model, just to sort of explain how it works. I think we're hopeful that it will be applicable in other scenarios. Sort of the most natural place is where your state space can be divided into these two, like a product space in the way that I showed, especially if they're nearly independent. That's sort of the key. If they're nearly independent, then this can give you quite a big advantage.
Okay, thanks. All right, other questions? Maybe also if you have a question, you can type it into the group chat and I can read it if you're shy about unmuting yourself. Okay, looks like we don't have any more questions. So thank you again, Amanda. And Oh, yeah. So would the next presenter please share their screen? I believe it's Shapir.
Sure.
Okay. And I encourage everyone to hide their video, just because it's nicer to give a talk to human beings rather than little black squares. So if you feel comfortable with it, please unhide your video feed. Okay, great. So this next talk will be given by Shapir Asadi, and he'll be telling us about palette sparsification beyond delta+1 coloring. Take it away, Shapir.
Okay, thanks. So everybody, can you hear me and see the slides? Okay, awesome. Okay, so I'm going to tell you about this palette sparsification problem, and this is joint work with Noga Alon. So a quick reminder on graph coloring. Here we have a graph G. We have this palette of colors 1 to C, and in a C coloring, we want to assign these colors to the vertices so that there is no monochromatic edges, like this one, for instance. Good. And through this talk, let me use n to denote the number of vertices, and delta is going to be my maximum degree. So arguably, the first thing you learn about graph coloring is that every graph can be colored with delta+1 colors, and the reason is trivial. You can just greedily color the graph, and you will never run out of color for each vertex. Good. So now let me ask you this question, which we called it palette sparsification. It's the following question. So originally in graph coloring, every vertex has this palette, the same palette of colors, and it can choose its color to, it can choose its color from that palette to color the graph. Now my question is that can you get these palettes and shrink their size to something much, much smaller, and still ask each vertex to pick its color from the smaller palette so that you can still color the graph, okay? So the only difference is that now each vertex choose its color from its shrunken palette. And the moment I pose this question, if you think about it, it's not an interesting question. Okay, sorry. Before that, let me show you an example. This is my graph. And that's the way I'm going to shrink the palettes. They're going to be something much, much smaller. And then I'm going to ask each vertex to color itself from just its smaller palette. Still, the graph should be monochromatic. There shouldn't be any monochromatic edges. Okay, good. So the problem with this question is that it's really not interesting. You can first look at your graph. You can find the coloring of the graph and then assign that color to each palette and then ask the person to color the graph. It's obviously possible. So the question I want to ask you is actually slightly different. Can you, without even looking at your graph, shrink its palettes to something much, much smaller, such that after that, when I reveal the graph, you are able to color the graph? And for you to have any chance, I'm going to allow you to use randomization, and it's going to be, I require that with high constant probability or with high probability, you should be able to still color the graph. So this is the problem I'm asking here. And to my knowledge, this was first asked in this joint work we had with Yu Chen and Sanjeev Khanna back in 2019, where we proved the following theorem. If I look at my graph, and for each vertex, uniformly at random and independently, I sample log n colors from 1 to delta+1, then we prove that we can still color the graph with high probability using these palettes. So we started with these very large palettes of size delta+1. We randomly shrunk them independently across the vertices into something smaller, and we said that still you can color the graph. Good. So that's this palette sparsification theorem of that work. And why we care about this question? First, on the surface, this seems like a very nice combinatorial question. But honestly, the reason we came up with this question was that it has some implication that allows us to design lots of interesting algorithms with completely non-trivial properties. For instance, it gave us the first semi-streaming algorithm for delta+1 coloring. Not going to define it, but basically it means that it's a space-efficient algorithm that can just read the edges of the graph once without even storing the edges and can find the color. And in fact, even more familiarly, it gives us an algorithm that allows us to delta+1 color a graph with randomization in n to the 3 half time. If you think about it, for dense graph, this is even faster than reading the graph once. Good. So with that in mind, now let's tell you, this is the motivation behind the current work. we saw that this palette of sparsification is a nice mathematical question and it has lots of applications. So let's just study it for other graph problems as well, okay? And that's what we are doing in this paper. And our results include studying this problem in a bunch of different regimes. One is that we asked that what will happen if I give you more than delta plus 1 color. Here we prove that if you have 1 plus epsilon delta colors for some constant epsilon, you can actually use only a square root log n samples per each vertex instead of log n, okay? And log n is known to be tight for delta plus 1. You can just show it by looking at collection of cliques. So this shows that you can actually there is a separation between these two problems when I go from delta plus 1 to 1 plus epsilon delta color. And a square root log n is again tight for this problem. So that was for using more than delta plus 1 colors. What if I want to work with some graphs that admit coloring with much less than delta plus 1 colors? And one such family is the family of triangle-free graphs that we know by this classical result of Johansson. They can be colored with delta over log delta colors. Okay, and again, this is tight asymptotically. Here we prove that we can shrink the size of each palette, not completely down to log n, but to any small polynomial in delta, while still getting asymptotically optimal number of coloring. So if you see there's this this gamma factor here, which appears here as well. We can reduce the size of each palette to delta to the 1 over 100, and then use roughly 100 times more number of colors than what is needed. And even though this sounds like a weird term here, now we have a polynomial dependence on delta, we prove that this is also necessary. So you need to pay for such a dependence for this result. And finally, we look at a version of the problem where the colors, the number of available colors for each vertex is not some global parameter, but a much local parameter, such as the degree of each vertex. Here, every vertex can start, to begin with, can only use colors 1 to its degree plus 1. And it's easy to see that still every graph can be colored this way, and we prove that by sampling log n colors, this is still possible. Cool. So that's for the result. And as a corollary of this result, we got tons of different sublinear algorithms. For instance, we got something for triangle-free graphs. Let me just mention that delta to the gamma factor that we had for triangle-free graphs also appears here in these applications. And a bunch of other sublinear algorithms. Some of them are based on this technique. Some of them are based on some generalization, which I'm not going to talk about. Finally, let me tell you very briefly what are the techniques. For the first two results, we actually found out some new connections between this palette sparsification theorem and very classical result on least coloring of graph due to Reed and Sodokov. And using those results and some of their generalization, we are able to prove these two. The lower bound that I mentioned for coloring triangle-free graphs is a new random graph theory argument. Yeah, which I found it interesting, and I'll talk briefly about it later. And then finally, for the log n, for using log n sample for degree plus 1 coloring, we again went back to this approach of ACK because this is a strict generalization of delta plus 1 coloring. And in fact, our proof closely follows ACK, except that we now have to use a different type of graph decomposition. Good. So that's really all I wanted to say. Let me conclude here. So these are our results. There are lots of open problems here. And let me just mention my favorite open problem. I told you this delta to the gamma term is necessary for palette sparsification of triangle-free graphs, and it bleeds out into our sublinear algorithms. But we don't know whether it is necessary for the sublinear algorithms or not. So far, all application of palette sparsification were beside this one gave out optimal algorithm, optimal sublinear algorithms as well, let's say in terms of time or space. This is the first time I don't know what is happening really. And I think it will be interesting to see whether either these problems can be solved using a better technique, or one can use our random graph theory argument, for instance, to prove a lower bound for this problem. And that's all I wanted to say, really. Thank you.
Okay, thank you for the nice talk. We have time, I think, for one question, if someone wants to unmute themselves and ask.
I have a question.
Sure.
So you have this big O of delta over gamma log delta colors, right? Like, do you need the big O there? Did you mean the big O there? Do you have to throw away some extra constant factors?
Yes, you have to throw out, like here, you have, so there is this recent result of molloy that gets 1 plus a small o of 1 delta over log delta. We cannot get that for any choice of delta. We need at least 9 or 10 as a constant here.
Okay, thanks again to Shapir, and let's have the next speaker share their screen. So next we'll have Jan Dreher telling us about maximum shallow clique minors and preferential attachment graphs have polylogarithmic size.
Oh, thank you very much. Everybody can see me, hear me, all fine? All right, great. So this is joint work by me together with Philipp Kuhnke and Peter Rosmanit. And we're going to talk about maximum shallow clique minors. And first, let's describe what the preferential attachment model is and why we care about it. So in a preferential attachment model, it works as follows. It's a random graph model, which iteratively constructs a random graph. You start with one vertex, and then you always add one vertex, a new one, and m edges. So here we have one vertex already with 2 edges. In this example, m is 2. We add one more vertex and 2 random edges. The random edges always start at the new vertex and then go somewhere to the network. And there's a rule by which the new edges are inserted. And the second endpoint of the new edge, the probability that any graph in the network is a second endpoint is proportional to the degree that the vertex in the network has already. For example, this vertex V3 has a degree of 3 now. This vertex has a degree of 6. So the probability that this edge here goes here is twice as high as it goes here. So you have a tendency that somebody who already has a high degree accumulates more degrees over time. So kind of like if you're on YouTube, you're more likely to click on a video which already has a bunch of views than a video which has no views. So if you iterate this process, let's say inserting 100 vertices, the network may look something like this. Here, these are the first vertices that have been inserted. They have a rather high degree. And on the right-hand side, those are the vertices which have been inserted in the end, and they have a very low degree. So somebody who's early to market will accumulate higher degree in the long run. And you can show that the expected degree of the ith vertex is roughly square root over n divided by I. So square root of n roughly for the first vertex and constant for the last vertex, more or less. And this behavior has been observed in many real-world networks. So the model has been proposed to simulate the degree evolution of the internet, and a similar inhomogeneous degree distribution has been observed in many real-world networks. And this is what makes the model interesting. It provides a rather simple, intuitive explanation on why networks grow the way they do and lead to the degree distribution that they have. So this is a model that we're working on, and we want to show asymptotic structural results on this model. And what we show is the following. We show that there's log n to the 1/4 many vertices, which are very highly connected. So they span a one subdivided clique. This means if you take any pair of them, there is one private vertex which connects both of them and is not adjacent to any other vertices. So these vertices are kind of as connected as it gets, at least in a subdivision. So you have a very densely connected cluster there. On the other hand, if you remove for some number r, log n to the O of r squared, n to the O of r, many vertices, like if you remove the early vertices of the random process, what you're left with is a very sparse graph. Here, the graph is, if you fix any vertex and the ball with radius r around it, what you're left with is basically a tree with at most 2 extra edges inserted in the graph. So the overall asymptotic structure of the preferential attachment model is you have a very densely connected core of size logarithmic roughly. And if you remove the first logarithmically many vertices, you get a very sparse graph in the end. So it's a nice complete picture that you get there. And now we may ask ourselves, why do you care about this? And most of you know that problems which are hard in general, they become more tractable if you consider simpler graphs. For example, problems are tractable on planar graphs, which are hard in general. And you can consider more general notions of simple graph classes. One of the most general notions would be nowhere denseness, which is complemented by the notion of somewhere denseness. And our results show that in the limit, preferential attachment graphs are here in this somewhere dense regime, meaning that the nice algorithmic techniques that you may have for planar graph or even for nowhere dense graphs, they don't work as you would like them to on preferential attachment graphs. So that means that a whole toolkit that is otherwise available for certain simpler graphs, we don't have it for a random graph model, assuming that we want to run algorithms on where the input is drawn from the preferential attachment model. And now some quick words on why we reach what nowhere denseness and somewhere denseness are. So these concepts are defined using subdivided cliques. So here you see an at most 3 subdivided clique of size 4. So you have 4 vertices, and on every edge at most 3 vertices have been inserted. And let's say we have a graph class G. And the question you ask is, how large is the largest at most R subdivided clique that is contained as a subgraph of any graph in the graph class G? And you have 2 possible answers here. Either this number is bounded for every value of R, then a graph class is said to be nowhere dense. And on the other hand, if the number is unbounded for every R, then it's said to be somewhere dense. And using the structural result, we can say something about the denseness of preferential attachment graphs. And so the largest subdivided clique at most are subdivided in preferential attachment graphs. So we see here, we have a 1 subdivided clique, which is log n to the 1/4. So it's not bounded, it grows steadily with the size of the network. If you insert more vertices, it gets bigger. So we can say that asymptotically, size of the largest at most R subdivided clique is polylogarithmic, somewhere between those 2 numbers. Meaning that in the limit, preferential attachment graphs are asymptotically somewhere dense, and the algorithmic techniques for nowhere dense graph classes or other sparse graph classes are not applicable in these graphs. Okay, thank you very much. That's all I had to say.
Thank you, Jan, for the nice talk. If someone has a question, feel free to unmute yourself and ask. I think we might have even time for 2 questions. Okay, I have a question.
Sure.
What is the size of the largest actual clique in a preferential attachment graph?
The size of the largest clique is bounded by the degeneracy of the graph. So you have some constant m, which is the number of edges that you insert per vertex. And this is something you usually assume to be a constant. And so it cannot be larger than m.
Okay, I see.
I'll also ask a question. Do people study the preferential attachment model when m is maybe some very slowly growing function of n, like log n or square root log n? Is it not interesting in that case? It just become too dense?
I think that's also interesting, and it would make sense to solve that, consider that, because m is kind of like the average degree, and it would make sense if the average degree is like log n, for example. And so, yeah, what we have is like a negative result. And even if m is like 2 or some small numbers, you already have these large cliques. So of course, if you blow it up, then it gets even denser. But in fact, this sparseness result, that if you remove a few vertices, the graph becomes sparse, that still holds if m is something like logarithmic.
Do you have a sense if the results will change very much if the number of edges that the arriving node is maybe like a Poisson distributed random variable rather than being a fixed number?
Oh, sorry, I don't have an intuition for that.
Okay, no worries. Okay, great. Thanks again, Jan, for the talk. Maybe the next speaker can share their screen. I believe it will be Prantar Ghosh.
Yeah, can you hear me?
Okay. Okay, so next we'll have Prantar Ghosh telling us about streaming verification for graph problems.
Yeah, can you see my screen? Can you hear me?
Not very well. Maybe you can get a little bit closer to your mic.
How about now?
For me, it's still a little bit faint, but it'll suffice if this is what we have.
Okay, I'll try unmuting myself. And is it better?
No.
Okay. Then I'll just start.
Okay.
Okay, thanks for the introduction. This is a joint work with my advisor Amit Chakravarti and Justin Thaler. So let me begin by telling you about the model we study. In the basic streaming model, a space-limited client downloads the data as a stream from a cloud repository, and he does stores only a summary of the data, does some computation on it, and then gives an output about the entire problem, about some problem on the entire data. But this memory restriction often yields some problems unsolvable, and that's why we study an enhanced model called the annotated streaming model, where the client can now outsource the data to a cloud service with unlimited memory. So the client, the cloud now needs to do the computation and send the answer to the client. So, but the cloud might have been hacked, or it might have incurred some hardware or network failure. So the client doesn't want to blindly trust it. So now this becomes a prover verifier system where the cloud, the prover, sends a help message or proof to the client who needs to verify its correctness using the summary of data he had stored. So he does some verification and computation on it, and then gives an output if he thinks that the cloud was honest, and otherwise rejects the proof. So such a protocol between prover and verifier is called a scheme. And the two complexity parameters we should try to optimize while designing a scheme are the size of the proof, that we call H cost, short for help cost, and the space used for verification and data processing, that we call V cost, short for verification cost. So scheme with order H cost and order V cost is called an H, V scheme. So this is the basic model. Now in this work we study graph streaming problems where the input is the stream of edges of an n-vertex graph, and we want to output some function of the graph. So the main problems that we study here are the triangle counting problem and the Max-Matchin problem, which is outputting the size of a maximum matching. So in basic streaming, it is known that these problems are hard. That is, you need to store almost the entire graph. That is, it requires omega n squared space, even if you are allowed multiple passes over the input. So what about the annotated model? Well, there's a lower bound here by Chakravarti et al. That says that any H, V scheme for these problems must have H times V at least n squared. So if you look at this lower bound curve, HV equals to n squared, we knew of only 3 upper bounds on them. So 1, n squared is trivial, and n squared, 1 and n, were given by prior work. So natural question is whether we can trade off H and V to attain more or maybe all points on this optimal trade-off curve. So our results make significant progress in answering this question. For any integer parameters t and s whose product is n, we give an s comma nt scheme for triangle counting, and that covers all the points on the upper half of this optimal trade-off curve, and an nt comma s scheme for maximum matching that covers all points on the lower half. For triangle counting, we also give an nt squared comma s scheme that doesn't quite achieve the optimal trade-off, but it does strictly better than what prior work had achieved for this h greater than n regime and gets closer to the optimal curve. So these are our main results. We also have a bunch of other results on graph problems, like for triangle counting in the edge arrival model, we have better schemes for sparse graphs. And we also have a new efficient scheme in the Vertex arrival model. For fundamental graph problems like maximal independent set, acyclicity testing in directed graphs, and topological sorting, we give optimal schemes that attain a smooth trade-off. And note that all these problems are hard in basic streaming, that is the equal omega n square space. Now, note that all these schemes follow by applications of a common framework of counting the number of edges in a collection of induced subgraphs. And we also have some results on shortest path related problems, such as ST shortest path, and both unweighted and weighted version of single store shortest path. Our results for single store shortest path weighted version are interesting for graphs of low diameter. Now, let me briefly tell you about the techniques that we use in this work to obtain these results, and on a very high level, how they helped us. So the Taylor in 2016 used the tool of nonlinear sketches, which is in contrast to the popular tool of linear sketches, where you store a sketch of some graph and then maintain it with the stream and update it as when the new edge arrives. You just update it. The update value depends only on the latest edge update. But for nonlinear sketches, the update value can also depend on the sketch of the graph that was stored so far. So these are nonlinear sketches, and Taylor showed that using such stronger sketches, you can obtain trade-off for these problems that are optimal. However, it wasn't smooth. So we used the technique Amit and myself used last year in random for vertex shaping, where we shape an n-sized vertex index vector into a two-dimensional T cross S array for some T and S whose product is n. So on a very high level, this is how we can split a cost of n into an h cost of T and phi cost of S for any T and S whose product is n, and obtain a smooth trade-off. But our scheme last year was suboptimal. So in this work, we kind of team up and succeed in combining our techniques to obtain a trade-off that is both optimal and smooth. So to summarize, we gave optimal trade-offs, we gave schemes with optimal trade-offs for multiple well-studied graph problems. We settled the complexity of triangle counting in the regime of h cost at most 10 and maximum matching in the opposite regime of h cost at least 10. For the latter regime, we gave improved schemes for triangle counting. And our scheme for the generic problem of induced edge count has various applications in fundamental graph problems. And finally, we gave a collection of interesting schemes for shortest path related problems. Thank you for listening. I'd be happy to take questions now.
Thanks, Prantar, for the nice talk. If anyone has a question, please feel free to unmute your microphone and ask.
So I have a quick question.
Mm-hmm.
So when you talked about optimal curves, one thing I think I missed, is it the case that all the optimal curves we know in this model are the form h cost times v cost is omega n square?
So for no, so let's say for the triangle counting and maximum matching problems, this is the lower bound. H times V is at least n squared. And so, but it follows that if some graph is intractable in basic streaming, like if it is omega n equals omega n squared space in basic streaming, then it would have this lower bound. So to speak more generally, if you know that the lower bound for a problem is omega s in basic streaming, then in this model, H times V should be at least s.
No, that's good. But can it be, for instance, H times V is even more than that? It's n.
Yeah, sure. So the lower bound can be much stronger, but we don't know any such lower bounds yet for any problem.
So optimal curve is the current lower bound. It's you.
Yeah.
Okay, got it.
So yeah, so for let's say for triangle counting and maximum matching, so we can show that the upper bound matches this lower bound. So we can get optimal things. But yeah, so for some problems where we don't know of such a lower bound, it's still open whether HV equals to n squared would be optimal or not.
Got it. Thanks.
Okay, thank you to all of the speakers in this session for the nice talks. And we'll be resuming. We're taking a break now until 11:20. We'll resume at 11:20 sharp. I guess for now we can go hang out in the Slack. Okay, so see you in 20 minutes.